Andromeda is already touching us, a massive envelope of gas stretching over 1 million light-years from its core has already reached halfway to our galaxy. We thought we knew this neighbor. We were wrong. The galaxy you can see with your naked eye is just the beginning. Recent discoveries reveal Andromeda is twice as large as we imagined, contains 1 trillion suns, and may not collide with us after all. If you're enjoying this deep dive into our cosmic neighbor, hit that like button and subscribe. Prepare yourselves. We begin. Look up on a clear autumn night. Find the constellation Cassiopeia, shaped like a W. Move your eyes slightly toward Perseus. You might see a faint smudge. That smudge is Andromeda. But here's what nobody tells you. What you're seeing is a lie. The visible part, that gentle blur of light, spans about 3 degrees across the sky, 6 times wider than the full moon. Already massive, already impossible to fully grasp. But scientists using NASA's Hubble Space Telescope discovered something that changes everything. Andromeda doesn't end where the light fades. It keeps going and going. In 2015, astronomers using the Space Telescope measured something previously invisible, a halo, not made of stars or planets, made of gas, hot, diffuse plasma stretching outward from the galaxy like an invisible ocean. This discovery came from Project Amiga, which stands for Absorption Map of Ionized Gas in Andromeda. The team used 43 quasars as background lights. Quasars are the brightest objects in the universe, powered by supermassive black holes, billions of light-years away. As their light traveled toward us, Andromeda's halo absorbed specific wavelengths. Each dip in brightness revealed the extent of the invisible envelope. The measurements were staggering. This halo stretches 1.3 million light-years from the galaxy's center. In some directions, it reaches 2 million light-years. If human eyes could see this gas, Andromeda would appear roughly 3 times the width of the Big Dipper. It would dominate the entire night sky, the biggest feature you'd ever witness. Every night, inescapable. This confirmed halo contains at least as much mass as half of all the stars in the galaxy itself. Think about that. 1 trillion stars burning in Andromeda's disk. The halo matches half that mass in pure gas. This isn't empty space. This is the galaxy's atmosphere, its breathing room, the material it uses to create new stars over billions of years. But there's something the scientists didn't expect, something that changes our entire relationship with this neighbor. The halo reaches halfway to the Milky Way. Our own galaxy likely has a similar envelope. The math is simple and terrifying. 1.3 million light-years from Andromeda, 1.3 million light-years from us, 2.5 million light-years apart. The halos are already touching. What we thought was a future collision has already begun. 2.5 million light-years separates us from Andromeda. Let me translate that distance into something your mind can hold. 1 light-year equals roughly 6 trillion miles. Multiply that by 2.5 million. You get 15 quintillion miles. 15 followed by 18 zeros. At highway speed, driving day and night without stopping, you'd need 44 trillion years to arrive. Yet, in cosmic terms, Andromeda is practically next door. It sits in what astronomers call the local group, a collection of roughly 100 known galaxies bound together by gravity. The Milky Way and Andromeda are the 2 largest members. Everything else orbits around them, like planets around twin stars. Between us and Andromeda lies mostly nothing. Intergalactic space, the void. Density drops to less than 1 atom per cubic meter. For comparison, Earth's atmosphere at sea level contains about 25 quintillion molecules per cubic meter. The space between galaxies is the closest thing to true emptiness that exists. Light crosses this void for 2.5 million years without hitting anything substantial. No planets, No asteroids, no clouds of gas, just occasional stray stars ejected from their home galaxies, wandering forever in the dark. But recent discoveries reveal the void isn't quite empty. Those halos we just discussed fill the space with thin plasma. Temperature reaches hundreds of thousands of degrees. Yet the gas is so sparse that you could pass through it without feeling anything. This material comes from both galaxies. When stars explode as supernovae, they blast heavy elements into space. Iron, carbon, oxygen, silicon, the building blocks of planets and life. Some of that material escapes the galaxy entirely. It drifts outward, cooling, spreading, forming the halo. Scientists confirmed something remarkable by studying this halo. It's layered. 2 nested shells surround Andromeda. The inner shell contains different elements and temperatures than the outer shell. This structure tells a story. The galaxy has been feeding on smaller neighbors for billions of years. Each meal added new material. Each merger stirred the halo like cream swirling in coffee. The layers are scars, evidence of countless ancient collisions. And buried in this halo are clues about what's coming next. The gas between us and Andromeda isn't static. It's moving, flowing, responding to the gravitational pull of both massive galaxies. Think of 2 whirlpools slowly spiraling toward each other in an ocean. The water between them begins churning long before the vortices touch. The halos are already interacting, but the visible galaxies haven't noticed yet. The collision has already started, not with a bang, not with stars crashing together or black holes roaring to life. It began quietly, invisibly, with gas. Project Amiga's findings, published in 2015 and updated through 2025, revolutionized our understanding. Using Hubble's cosmic origin spectrograph, the team mapped Andromeda's halo in unprecedented detail. They measured not just its size, but its composition. The halo contains huge amounts of heavy elements: oxygen, carbon, nitrogen, silicon, and sulfur, all forged inside stars and ejected during their deaths. Over Andromeda's lifetime, nearly half of the heavy elements created by its stars have been expelled beyond the visible disk. The galaxy has essentially been bleeding metal into space for billions of years. This enriched gas spreads outward at hundreds of miles per second. Some escapes forever. Some eventually falls back, recycled into new generations of stars. This is how galaxies breathe. But here's the critical discovery. Andromeda's halo extends 1.3 million light-years in our direction. The Milky Way sits 2.5 million light-years away. Since the Milky Way and Andromeda are similar in size and type, scientists assume our galaxy has a comparable halo. The math becomes unavoidable. Both halos extend roughly 1.3 million light-years. Added together, that's 2.6 million light-years. They overlap. We cannot easily study the Milky Way's halo from inside it. It's like trying to understand the shape of a forest while standing among the trees. Everything blocks your view. But by studying Andromeda, we're looking at our own future. These 2 galaxies are cosmic twins. Similar mass, similar structure, similar history. What's true for one is likely true for the other. The overlap zone represents something unprecedented. 2 galactic halos mixing together, their gases interacting on scales we can barely measure. This interaction is subtle. The densities are so low that nothing dramatic happens yet. But gravity never stops working. Every particle of gas in both halos feels the pull of both galaxies. Over millions of years, this pull will grow stronger. Think of it like 2 soap bubbles floating toward each other. Long before the thin films touch, air currents between them begin to shift. Forces we can't see prepare for the inevitable moment of contact. The bubbles don't realize they're doomed. They just drift closer. The halos touching means the merger isn't some distant future event. It's happening right now. We're living inside the opening act of a cosmic collision that will take billions of years to complete. But how fast is Andromeda actually moving toward us? And what will happen when the solid parts finally meet? Andromeda dwarfs the Milky Way. For decades, scientists believed the opposite. They thought our galaxy was the larger of the two, more massive, more stars, more dominant. New measurements shattered that assumption. The visible disk of Andromeda spans roughly 200,000 light-years across. The Milky Way measures about 100,000 light-years in diameter. Andromeda is twice as wide. But that comparison only includes the bright disk where most stars live. When you factor in the full extent, including the halo, Andromeda's true diameter reaches 2 million light-years. It's a monster. This galaxy contains approximately 1 trillion stars. The Milky Way holds between 200 and 400 billion stars. Andromeda has at least twice as many suns burning in its spiral arms, maybe 3 times as many. Each star potentially hosts planets. Each planet might harbor moons. The sheer scale of matter, organized into one gravitationally bound system, defies comprehension. NASA's Hubble Space Telescope captured the most detailed image of any external galaxy ever taken. The panchromatic Hubble Andromeda Treasury, called PAT, required over 400 individual pointings of the telescope. 7,398 separate exposures taken from July 2010 through October 2013. The final mosaic contains 1.5 billion pixels. It shows over 100 million individual stars in just a 61,000 light-year section of the disk. 100 million stars in one photograph, and that's less than 1/3 of the galaxy. The resolution is so extreme that you can see individual blue giants, red supergiants, and star clusters embedded in dust lanes. It's like photographing a beach and resolving individual grains of sand, except the beach is larger than anything humans will ever visit. The stars in that image are so far away their light has been traveling for 2.5 million years. When that light began its journey, early human ancestors were just learning to make stone tools on Earth. Andromeda's mass tells an even more dramatic story. For years, astronomers assumed it was 50% more massive than the Milky Way. Recent calculations using escape velocity and dynamical measurements changed everything. As of 2019, Andromeda's total mass, including dark matter, comes in at about 0.8 trillion solar masses. The Milky Way, surprisingly, weighs 1.5 trillion solar masses. Our galaxy is actually heavier, but Andromeda has more visible stars, more light, more structure. This creates a puzzle. Andromeda looks bigger, but weighs less. The answer lies in dark matter distribution, the invisible matter that makes up most of both galaxies. Our galaxy apparently has a more massive dark matter halo, even though Andromeda's visible components are larger. It's like comparing two icebergs. One shows more above water, but the other has a more massive hidden bulk beneath the surface. Yet even with these measurements, both galaxies are still being studied, and the numbers keep changing. Imagine 1 trillion stars. Not 100, not a million, 1 trillion. A number so vast that if you counted 1 star per second, never sleeping, it would take 31,700 years to finish. And these aren't just dim embers. Many of these stars burn brighter and hotter than our sun day. Andromeda's stellar population spans the entire range of stellar life. Blue giants radiating temperatures over 30,000 degrees Celsius dominate the spiral arms. These monsters live fast and die young. They burn through their hydrogen fuel in just a few million years before exploding as supernovae. Then come the yellow dwarfs like our Sunday stable, long-lived, burning for billions of years. The galaxy's center glows with ancient red giants, stars that have already exhausted their core hydrogen and swelled to enormous sizes. Some of these red giants are large enough to swallow Earth's orbit if placed at the sun's position. The spiral arms themselves are construction zones. Massive clouds of hydrogen gas collapse under their own gravity. Temperatures at the cores reach 15 million degrees. Nuclear fusion ignites. a new star is born. This process happens constantly. Andromeda creates stars at a rate of about 1 solar mass per year. That means every year, enough gas collapses to form 1 star equivalent to our Sunday, or 2 smaller stars, or 1 massive blue giant. Between the stars lies dust, lots of dust. Hubble images show dark lanes threading through the bright spiral arms. These aren't empty regions. They're dense clouds of particles smaller than bacteria. Silicon grains, carbon soot, ice crystals. This dust absorbs visible light but glows in infrared wavelengths. NASA's Spitzer Space Telescope revealed the true extent of these dust structures. Long filaments spiral inward toward the galaxy's center. Some stretch thousands of light years. The stars aren't distributed, clouds slam together. The impact triggered an enormous burst of star formation. For roughly 100 million years, Andromeda created stars at 10 to 100 times its current rate. It became what astronomers call a luminous infrared galaxy, a cosmic furnace. That ancient collision left permanent scars in the stellar population. You can see them in the age distribution. A huge number of stars in the disk are about 2 billion years old. They all formed during that violent epoch when the merger peaked. These stars orbit in strange patterns, still carrying the momentum from their chaotic birth. All those suns, all that light, all that history, and at the very center, something hungry waits. The black hole at Andromeda's core masses 110 million times our Sunday, compressed into a region smaller than our solar system. This object, designated M31 star, or M31 asterisk, sits in the exact gravitational center of the galaxy. Everything else orbits around it. Unlike the supermassive black holes that power quasars and active galaxies, Andromeda's central beast is quiet, eerily quiet. Astronomers classify it as a low-luminosity, active galactic nucleus. It emits very little radiation, considering its enormous mass. The black hole at the center of the Milky Way, Sagittarius A star, is even quieter. Both are cosmic hermits, barely eating, barely glowing. But quiet doesn't mean inactive. The Chandra X-ray Observatory has monitored Andromeda's core continuously since 2009. These observations revealed something unexpected. The black hole flickers, not like a light switch, more like a candle in a drafty room. The X-ray output remains relatively constant for years, then suddenly spikes. In 2006, a flare erupted. Brightness increased dramatically. The elevated state lasted for years. Then in 2013, another flare burst from the core. Dr. Stephen DeKirby and his team at Michigan State University analyzed 15 years of Chandra data published in 2025. They tracked 4 X-ray sources near the galaxy's center. One source, called P2, sits at the exact position of the supermassive black hole. The other 3 sources remain mysterious. By carefully separating the signals, the team created a complete light curve showing how the black hole's brightness changed over time. The flares tell us the black hole is eating. But eating what? NASA's Spitzer Space Telescope found the answer. Long spiral streams of dust and gas flow inward from thousands of light years away. These filaments follow precise paths carved by gravity. They spiral closer and closer, like water circling a drain. As the material approaches the black hole, friction heats it to millions of degrees. The hot gas glows in X-rays. When the feeding rate stays constant, the X-ray brightness stays constant. When clumps of gas fall in, the brightness flares. Recent research, published in the Astrophysical Journal in 2023, revealed exactly how this feeding works. Computer simulations showed that a small disk of hot gas forms just outside the black hole. The disk is replenished by numerous streams from farther out. If the streams stay within certain size and flow rate limits, the black hole remains quiet. Feed it too much, too fast, and it reacts violently. The radiation output skyrockets. Strong winds blow gas away. star formation in the surrounding region shuts down. Andromeda's black hole feeds carefully. The streams detected by Spitzer fit perfectly within the constraints for steady accretion. The black hole consumes about 1/10,000th of a solar mass per year. Sounds tiny, but over millions of years, it adds up. The temperature of the gas falling in surprised everyone. Most supermassive black holes heat their food to tens or hundreds of millions of degrees. Andromeda's black hole, just a few million degrees, cool by cosmic standards. Something about this galaxy's feeding process is different, and scientists still don't fully understand why. Andromeda is a crime scene. The evidence is everywhere once you know how to look. The galaxy we see today is not the galaxy that existed 5 billion years ago. Something violent happened, something that left permanent marks on the stellar population and structure. Between 2 and 3 billion years ago, confirmed through multiple studies, a massive merger occurred. Two galaxies collided. One was the original Andromeda, the other was roughly 1/4 its mass. The smaller galaxy plunged into the larger one. Their dark matter halos overlapped first. Then their gas clouds crashed together at hundreds of miles per second. Shock waves rippled through both galaxies. The impact compressed gas to densities that triggered runaway star formation. For approximately 100 million years, Andromeda blazed as a luminous infrared galaxy. Star formation peaked at rates 10 to 100 times higher than today. Thousands of massive stars were born every year. The galaxy glowed with the combined light of hundreds of billions of young, hot stars. If any civilizations existed in either galaxy at that time, their skies would have been dominated by spectacular star-forming regions and frequent supernovae. The evidence for this merger comes from multiple sources. First, the age-velocity dispersion relation. Stars in Andromeda don't move the way they should if the galaxy had evolved peacefully. Older stars orbit faster than expected. Younger stars show strange velocity patterns. This anomaly only makes sense if a large population of stars was violently stirred by a merger about 2 billion years ago. Second, the star formation history. Astronomers can determine when stars formed by measuring their spectra and comparing to stellar evolution models. A huge spike appears around 2 billion years ago. Far more stars formed during that period than in the billions of years before or after. Third, the structure itself. Computer simulations by multiple research teams showed that a merger with a mass ratio of approximately 4:1 perfectly explains Andromeda's current appearance. The models reproduce the extended thick disk, the young thin disk, the prominent bulge, and even the strange ring-like features visible in certain wavelengths. The merger also explains the giant stellar stream arc visible in the outer halo. That stream is debris, the shredded remains of the smaller galaxy, torn apart by tidal forces. The collision injected enormous amounts of heavy elements into the halo. Supernovae from the burst of star formation blasted iron, oxygen, and other metals into space. Over Andromeda's lifetime, this process expelled nearly half of all the heavy elements ever created by its stars. The halo we discussed earlier is enriched because of this ancient violence. But Andromeda didn't stop there. It's currently devouring its companion galaxy M32. M32 was once a normal spiral galaxy. Now it's a compact elliptical, stripped, cannibalized. Most of its outer stars were stolen by Andromeda's gravity. The process is ongoing. M32 is shrinking every million years. Galaxies are not peaceful islands. They're battlefields where smaller victims get consumed by larger predators. Look at Andromeda in ultraviolet light. The visible spiral arms disappear. In their place, something strange emerges. Rings. Multiple concentric rings of young, hot stars encircling the galaxy's core. These features shouldn't exist in a normal spiral galaxy. NASA's Galaxy Evolution Explorer, GALEX, captured stunning ultraviolet images that revealed the true extent of these rings. They glow blue-white. Each ring contains neighborhoods of massive stars. Temperature exceeds 30,000 degrees Celsius. These stars are extremely young by cosmic standards, just a few 100 million years old, mere infants compared to the galaxy's age of 10 billion years. The rings are evidence of collision. When Andromeda merged with another galaxy 2 billion years ago, the impact sent ripples through the disk. Imagine dropping a stone into still water. Waves spread outward in circles. In a galaxy, the waves are density waves. They compress gas as they pass. Compressed gas collapses under its own gravity. New stars form in ring patterns following the wave. But there's another interpretation. Some researchers propose the rings came from a different event. About 200 million years ago, Andromeda may have collided directly with its smaller companion M32. Computer simulations, using NASA's Spitzer Space Telescope data, suggest this encounter could explain the ring structure. The collision would have been glancing, not a full merger, just enough to disturb the gas and trigger a burst of star formation that organized itself into rings. The rings are clearest in ultraviolet because that wavelength reveals the hottest, youngest stars. In visible light, the rings blend with the spiral arms. In infrared, they almost vanish. The dust lanes between spiral arms show up starkly against the bright rings when viewed in ultraviolet. These dark lanes trace regions where star formation is happening right now. Eventually, stellar winds from newly born stars will blow the dust away. The lanes will brighten. The cycle continues. One particular ring structure stands out, a 10 kiloparsec ring. That's roughly 33,000 light-years from the center. This ring contains enormous amounts of star-forming gas. Multiple studies confirmed its existence through radio observations of neutral hydrogen. The ring rotates around the galaxy but doesn't follow the expected pattern. Its orbit is tilted, eccentric, again pointing to a violent origin. The discovery of these rings changed how astronomers understand galaxy evolution. Spirals aren't just slowly rotating disks that gradually form stars over billions of years. They're dynamic systems shaped by collisions. Each major impact leaves fingerprints that last for hundreds of millions of years. Andromeda's rings are fossils, evidence of trauma embedded in the stellar population, and astronomers know at least 2 more major collisions are coming, one with the triangulum galaxy M33 and one with us. Each impact will create new rings, new bursts of star formation, new scars that future astronomers might study billions of years from now, if any astronomers survive to see them. Andromeda is moving, not drifting, plunging toward us at 68 miles per second. That's 245,000 miles per hour, fast enough to circle Earth 10 times in 60 minutes. This velocity was first measured over 100 years ago, using spectroscopy. In 1912, astronomer Vesto Slipher used the Lowell Observatory in Arizona to measure Andromeda's radial velocity. He found it was approaching at about 300 kilometers per second, which equals 186 miles per second. Later refinements corrected this number. Current measurements using the Doppler effect place the approach velocity at roughly 110 kilometers per second. That's 68 miles per second. Blue shift in the galaxy's spectrum confirms it's moving toward us, not away. Blue shift occurs when an object moves toward you. The motion compresses the wavelengths of light it emits. Blue light has shorter wavelengths than red light, so approaching objects appear slightly bluer than they actually are. The effect is tiny for galaxies, but modern spectrographs can measure wavelength shifts to extreme precision. The measurements are unambiguous. Andromeda is coming, but velocity alone doesn't predict collision. You need to measure sideways motion too. Radial velocity tells you how fast something approaches along your line of sight. Proper motion tells you how fast it's moving across the sky. If Andromeda has significant proper motion, it might zip past us like a car speeding down an adjacent highway lane. If proper motion is 0, we're directly in its path. For over a century, astronomers couldn't measure Andromeda's proper motion. The galaxy is too far away. Even at 2.5 million light-years, which is close for a galaxy, the angular movement across the sky is incredibly small, less than 1,000th of an arcsecond per year. Earlier telescopes lacked the precision. Then came Hubble. Between 2002 and 2010, the Space Telescope repeatedly photographed the same regions of Andromeda, not the whole galaxy, specific star fields. By comparing the positions of individual stars against distant background galaxies billions of light-years away, astronomers could measure tiny shifts. They averaged measurements across thousands of stars to achieve sub-pixel accuracy. The results came in 2012. Dr. Roland van der Marel led the team at the Space Telescope Science Institute. Their findings were definitive. Andromeda's proper motion is consistent with zero given measurement uncertainties. The galaxy is moving almost directly toward us. The sideways component, if any, is too small to matter. A head-on collision appeared inevitable. The announcement made headlines worldwide. Scientists created computer simulations showing what would happen. The galaxies would begin a series of close passes over billions of years. Each pass would distort both galaxies through tidal forces. Stars would be flung into new orbits. Gas clouds would collide and trigger massive star formation. Eventually, around 4 to 5 billion years from now, the galaxies would merge completely. They'd form one giant elliptical galaxy. Astronomers nicknamed it Milkomeda or Milkdromeda. For over a decade, this prediction stood unchallenged. Textbooks declared the collision certain. Documentaries showed dramatic simulations. The merger became scientific consensus. Then, in 2025, everything changed. The collision might not happen. New research, published in June 2025 in the journal Nature Astronomy, overturned decades of certainty. Dr. Till Sawala from the University of Helsinki led an international team that re-examined every assumption. Their conclusion: we have approximately a 50% chance of avoiding the merger entirely. 50-50. A coin flip. Our galaxy's fate hangs in perfect balance. The team used the latest data from both Hubble and the European Space Agency's Gaia spacecraft. Gaia has measured the positions and motions of over 1 billion stars in the Milky Way with unprecedented precision. Combined with Hubble's measurements of Andromeda, the team had the most comprehensive dataset ever assembled. But data alone wasn't enough. They needed to account for uncertainties. Previous studies assumed most likely values for unknown quantities: distance uncertainties, mass uncertainties, velocity uncertainties. Each assumption seemed reasonable individually, but small errors compound. When you multiply many uncertain measurements together, the final uncertainty grows enormous. Sawala's team took a different approach. They ran 100,000 computer simulations. Each simulation varied the input parameters within their measurement uncertainties. Some runs assumed Andromeda was slightly more massive. Others assumed it was lighter. Some placed it closer, others farther away. The simulations included gravitational effects from other local group galaxies, not just the big two. This is where things got interesting. Previous studies treated Andromeda and the Milky Way as an isolated pair, two galaxies alone in space. But the local group contains about 100 known galaxies. Most are tiny, dwarf galaxies with just millions of stars, too small to matter, but a few are substantial enough to affect the dance between giants. The team focused on two in particular: the Triangulum Galaxy, M33, and the Large Magellanic Cloud. M33 orbits Andromeda as a satellite. The Large Magellanic Cloud orbits the Milky Way. Both are much smaller than their hosts, but both have enough mass to subtly alter trajectories through gravitational influence. Here's what the simulations revealed. M33 increases the merger probability. Its gravitational pull tugs on Andromeda, guiding it slightly more toward the Milky Way. The effect is small but measurable over billions of years. If M33 was the only factor, the collision would remain almost certain. But the Large Magellanic Cloud does the opposite. Its orbit runs perpendicular to the Milky Way and Andromeda collision path. As it circles our galaxy, it pulls us sideways, away from Andromeda, not by much. Just enough to introduce doubt. The Large Magellanic Cloud contains only about 15% of the Milky Way's mass. That tiny fraction is sufficient to change our fate. The simulations played out over 10 billion years of simulated time. In just over half the runs, the galaxies experienced an initial close pass. Their halos interacted, the encounter sapped orbital energy. Eventually, they fell back together and merged into one elliptical galaxy. But in slightly less than half the runs, the galaxies swung past each other at a safe distance. They remained separate forever. The probability isn't exactly 50-50. The team calculated approximately a 50% chance of merger within the next 10 billion years. Only about a 2% chance the collision happens in the previously predicted timeframe of 4 to 5 billion years. Most merger scenarios now fall between 8 and 10 billion years in the future. This changes everything we thought we knew about our cosmic neighborhood. The Large Magellanic Cloud looks like a smudge in the southern sky, a satellite galaxy orbiting the Milky Way. Visible to the naked eye from the southern hemisphere, it contains roughly 30 billion stars, tiny compared to our galaxy's 300 billion, barely 15% of the Milky Way's mass. You'd think something so small wouldn't matter. You'd be wrong. The Large Magellanic Cloud orbits perpendicular to the plane where Andromeda is approaching. Imagine looking down at the solar system from above. Planets orbit in a relatively flat disk. Now, imagine a comet plunging toward the Sun from high above that disk, almost straight down. The Large Magellanic Cloud's orbit is tilted like that compared to Andromeda's approach vector. This orientation creates a critical effect. As the Large Magellanic Cloud circles the Milky Way, its gravitational pull tugs on our galaxy, not forward or backward along the collision path, sideways, perpendicular. The effect is like someone gently pushing your shoulder while you're walking toward a doorway. One small push doesn't change your direction much, but continuous pushes over an hour, you'll veer off course. Sawala's team discovered that this sideways pull is enough to reduce the collision probability. In simulations without the Large Magellanic Cloud, merger rates climbed above 70%, including it drops the rate to roughly 50%. One small satellite galaxy alters the fate of two giants. But the story gets stranger. The Large Magellanic Cloud won't remain a satellite forever. Simulations show with near certainty that within the next 2 billion years, it will spiral into the Milky Way. The orbit is decaying. Each pass brings it closer. Eventually, it will plunge into our galactic disk. The collision will be catastrophic. Gas clouds will slam together. A burst of star formation will erupt across the impact zone. The merger will add 30 billion stars to the Milky Way's population. This merger will also alter the Milky Way's motion through space. When the Large Magellanic Cloud finally falls in, its momentum will be absorbed. The impact will change our velocity, our trajectory. How this affects the potential Andromeda collision remains uncertain. The timing is critical. If the Large Magellanic Cloud merges before Andromeda arrives, the sideways pull vanishes. Our trajectory changes. This could push us back toward Andromeda or farther away, depending on the exact details. The researchers admitted that even with 100,000 simulations, predicting 10 billion years into the future involves enormous uncertainty, too many variables, too many small forces accumulating over vast timescales. They compared it to weather forecasting. Meteorologists can predict tomorrow's weather with high confidence. Next week becomes uncertain. Next month is nearly impossible. Next year, forget it. The chaos of interacting systems makes long-term prediction fundamentally limited. Galaxies have even more complex interactions than weather systems, not just two objects orbiting each other. Hundreds of factors, dark matter distribution, ongoing mergers with dwarf galaxies, the gravitational influence of the entire local group. Each factor introduces uncertainty. Stack them all together and the future becomes murky. Yet the research reveals something profound. The universe doesn't follow predetermined scripts. Small objects can change the fate of giants. Tiny satellites can prevent apocalyptic collisions or cause them. The cosmic dance is more chaotic and beautiful than we imagined. Whether Andromeda collides with us or not, the Large Magellanic Cloud will definitely collide with us. That merger is coming. The halos are already merging. This isn't speculation. It's confirmed fact based on measurements published between 2015 and 2025. The question isn't whether the halos are interacting. The question is what happens next. When two galactic halos overlap, the physics gets complex. Both halos contain hot plasma. Temperatures range from hundreds of thousands to millions of degrees Celsius. The gas is ionized. Atoms have been stripped of electrons by heat and radiation. This creates a charged soup of particles that responds to gravity, pressure, and magnetic fields. As the halos interpenetrate, several things happen. First, gravity from both galaxies acts on the gas. Material in the overlap zone feels pull from two directions. Some gas will eventually fall into Andromeda. Some will fall into the Milky Way. The rest will remain suspended between the galaxies, forming a bridge of hot plasma connecting the two. Second, pressure differences create flows. Gas naturally moves from high-pressure regions to low-pressure regions. The halos aren't uniform. They're denser near the galactic centers and more diffuse at the edges. Where they overlap, pressure gradients will drive circulation. Think of it like two weather systems merging. The interaction creates winds, turbulence, complex flow patterns that take millions of years to play out. Third, magnetic fields tangle together. Both galaxies have magnetic fields threading through their halos. These fields are weak but organized over enormous volumes. When the halos merge, the magnetic fields interact. They can amplify each other. They can cancel out. They can twist into complex knots. Charged particles follow magnetic field lines. So, the field geometry determines where gas flows. The observable effects of this halo merger are subtle. You can't see it in visible light. The gas is too hot and too sparse to glow brightly. But ultraviolet and X-ray telescopes can detect the signatures. Certain spectral lines appear when hot gas absorbs light from background quasars. By comparing the absorption features from different sightlines, astronomers map the density and temperature distribution. Project Amiga did exactly this. They used 43 quasars scattered behind Andromeda at different angles. Each quasar's light passes through a different path through the halo. By measuring absorption in each spectrum, the team created a three-dimensional map. The map shows not just extent, but also internal structure, layering, clumps, streams. Some regions of the halo move toward us, others move away. The velocity structure reveals how gas is flowing. Some flows are simple, following gravity toward the galactic centers. Other flows are chaotic, stirred by ancient collisions and mergers. The halo is not a static atmosphere. It's a dynamic, evolving system. As the Milky Way's halo and Andromeda's halo continue to interpenetrate, the combined system will grow larger, more massive, hotter. Eventually, if the galaxies merge fully, the two halos will become one, a single enormous envelope surrounding the merged galaxy. That combined halo would extend several million light-years in all directions. It would dominate the local group. Smaller satellite galaxies would swim through it like fish in an ocean. But even if the galaxies don't merge, even if they pass each other and separate, the halo interaction will leave permanent marks. Gas stripped from one galaxy will enrich the other. Heavy elements will mix. The chemical composition of future stars will reflect this exchange. The merger of halos is the first act. The merger of stars comes later. Milkomeda. the name given to the hypothetical merged galaxy that would result from an Andromeda and Milky Way collision. Some prefer Milkdromeda. Neither name sounds particularly dignified for such a momentous cosmic event, but the name is the least interesting thing about this potential future. If the merger happens, computer simulations reveal the step-by-step process. First contact occurs when the two galactic disks pass through each other. This isn't a collision in the usual sense. Stars are so far apart that individual stellar collisions are virtually impossible. The average distance between stars is about 100 billion miles. Even in dense regions near galactic centers, stars maintain separation of billions of miles. When two galaxies merge, stars pass between each other like two clouds of gnats flying through each other. No impacts, just complicated gravitational interactions. But gas clouds do collide. Gas is more continuous. When two giant molecular clouds slam together at hundreds of miles per second, shockwaves compress the gas to extreme densities. Temperature spikes. Pressure skyrockets. Within millions of years, massive star formation erupts across the collision zones. This is called a starburst. The merged galaxy would temporarily become a starburst galaxy. Millions of new stars would form per year. The galaxy would blaze with ultraviolet light from young, hot stars. The burst would last perhaps 100 million years. Then gas reserves would deplete. Star formation would drop back to normal rates or lower. Many massive stars born during the starburst would already have died as supernovae. Their explosions would seed the interstellar medium with heavy elements. Future generations of stars would be more metal-rich because of this epoch. The final product, according to simulations, would be a giant elliptical galaxy, not a spiral. Spirals require organized rotation, disks of stars orbiting in the same direction. When two spirals merge, the collision randomizes stellar orbits. Stars end up moving in all directions. Some orbit clockwise, some counterclockwise, some plunge radially in and out. The chaotic motion produces an elliptical shape, a football-shaped blob of stars with no distinct spiral arms or disk. The merged galaxy would contain about 1.3 trillion stars, combined population from both progenitors. It would span about 200,000 light-years across in its densest regions. Larger if you count the extended halo. Total mass, including dark matter, would approach 2 trillion solar masses. This would make Milkomeda one of the larger galaxies in the local group, not a giant by cosmic standards, but substantial. At the center of this new galaxy, two supermassive black holes would orbit each other. The Milky Way's black hole masses 4 million solar masses. Andromeda's masses 110 million solar masses. Combined, they'd create a binary black hole system with 114 million solar masses. The two would spiral closer over tens of millions of years, emitting gravitational waves. Finally, they'd merge. The collision would release more energy in gravitational waves than all the stars in the galaxy emit as light over the same time period. The merged black hole would settle at the new galaxy's gravitational center. Our solar system would likely survive the merger physically intact. The chances of another star passing close enough to disrupt planetary orbits are extremely low, but our location would change. Simulations suggest a 50% probability we'd be flung 3 times farther from the galactic center, a 12% chance we'd be ejected from the galaxy entirely, thrown into intergalactic space, forever. None of this matters for Earth. By the time any merger occurs, our planet will already be uninhabitable. The sun gradually brightens as it ages. In about 1 billion years, increased solar radiation will boil Earth's oceans. All life will end, but the merger would be spectacular to watch from somewhere else. Andromeda's center is strange. The galaxy has 2 bright nuclei. Not 1, 2. This double nucleus has puzzled astronomers since its discovery by the Hubble Space Telescope in 1991. The brighter concentration, designated P1, sits offset from the true gravitational center of the galaxy. It contains mostly older, cooler stars, yellow and red giants that have been shining for billions of years. P1 appears as a compact elliptical cluster, very dense, millions of stars packed into a region just a few light years across. The dimmer concentration, P2, sits at the actual center. This is where the supermassive black hole lives. P2 contains a strange population of stars. Many are hot, blue A-type stars. These stars are young, just a few 100 million years old. Finding young stars so close to a supermassive black hole is unusual. The tidal forces near a black hole should prevent star formation. Something created these stars despite the hostile environment. Within P2 sits an even more compact structure called P3. This is an embedded star cluster containing many ultraviolet bright A stars. They orbit the supermassive black hole in an eccentric disk. Not a circular disk like you'd expect. The orbits are elongated. Stars linger at the farthest point from the black hole, called apocenter, creating a concentration of stars in one region. This eccentric distribution suggests a violent origin. One hypothesis proposes the eccentric disk formed from a previous black hole merger. If Andromeda's central black hole swallowed another black hole in the past, the merger would have released enormous amounts of energy as gravitational waves. Those waves could have kicked nearby stars into eccentric orbits. The pattern we see today would be the aftermath of that ancient event. Another mystery: why is P1 offset from the center? When the double nucleus was first discovered, astronomers thought P1 might be the core of a small galaxy that Andromeda had recently cannibalized. A leftover nucleus falling toward the center. But this idea has problems. Such a nucleus would have an extremely short lifetime. Tidal forces from the central black hole would rip it apart within a few million years. P1 has been there for much longer. The current understanding is that P1 is not a separate object. It's part of Andromeda's nucleus. The offset occurs because of the eccentric disk in P2. The disk's eccentricity creates an asymmetry in the mass distribution. This asymmetry shifts the apparent center of light away from the gravitational center. P1 is essentially a side effect of the weird stellar orbits in P2. Spectroscopic observations confirmed that P1 doesn't contain its own black hole. The velocity distribution of stars in P1 doesn't show the signature of a compact, massive object at its center. If learning to read those stories by combining observations with detailed computer simulations, Andromeda's nucleus will become even more complex when the Milky Way arrives. If the merger happens, our galaxy's central black hole will dive toward Andromeda's. The two will dance around each other for millions of years before finally coalescing. That merger will stir the stellar population near both nuclei. It will create new eccentric orbits, new asymmetries. Perhaps future astronomers studying the merged galaxy billions of years from now will look at its center and wonder what created such a strange configuration. They'll be looking at evidence of our collision. Andromeda is not alone. Two prominent companions orbit the giant spiral, M32 and M110. Both are satellite galaxies. Both are doomed. M32 is the brighter of the two, a compact elliptical galaxy sitting just 190,000 light-years from Andromeda's center. That's closer than the edge of Andromeda's main disk. M32 contains a few billion stars. It appears as a small, bright blob when viewed through telescopes. Unremarkable, forgettable. But M32 has a tragic story. This galaxy was once much larger, probably a normal spiral, similar to the Milky Way. It orbited Andromeda at a safe distance for billions of years. Then, something changed. Orbital mechanics brought it closer. As M32 passed through Andromeda's outer regions, tidal forces began stripping stars away. The outer layers of M32 were torn off, star by star, gas by gas. all stolen by Andromeda's vastly stronger gravity. The stripping process took billions of years. It's still happening now. Each orbit brings M32 through Andromeda's disk. Each passage strips away more material. The galaxy is shrinking, dying. Eventually, nothing will remain except its dense core. That core might survive as a globular cluster orbiting Andromeda forever, or it might be completely absorbed, merged into the giant galaxy's stellar halo. Evidence of this cannibalization appears in Andromeda's outer structure. Streams of stars stretch through the halo. These are tidal tails, long filaments of stars pulled from M32 during close passages. Astronomers trace these streams across hundreds of thousands of light years. They follow curved paths shaped by gravity. Each stream marks an orbit, a scar from an ancient passage. M110 sits farther out, about 800,000 light-years from Andromeda's center. It's larger than M32, but much dimmer. A dwarf elliptical galaxy containing several billion stars. M110 appears elongated, distorted. Tidal forces from Andromeda are stretching it like taffy. This galaxy is also being slowly devoured. Its fate is sealed. But Andromeda has more than 2 satellites. The Pan-Andromeda Archaeological Survey, or P&AS, discovered dozens of faint dwarf galaxies orbiting the giant. Most are extremely dim, just a few thousand stars each. They're so sparse that they appear more like loose clusters than galaxies. These ultra-faint dwarfs orbit in the outer halo, protected by distance. For now, interestingly, many of Andromeda's satellites orbit in a disk-like structure, not scattered randomly in all directions. They follow a preferred plane. This suggests they were captured in a coherent group. Perhaps they all came from a larger galaxy that Andromeda destroyed billions of years ago. The fragments became satellites, still orbiting in the same plane they occupied when they arrived. The distribution of satellites tells us about dark matter. Each dwarf galaxy should have its own dark matter halo. By measuring how fast satellites orbit, astronomers can infer the total mass of Andromeda, including its dark matter. The measurements consistently show that Andromeda's dark matter halo extends at least 700,000 light-years, possibly over 1 million light-years. The visible stars occupy just a tiny fraction of the total gravitational structure. When the Milky Way and Andromeda eventually interact, whether they merge or not, their satellite galaxies will be thrown into chaos. Orbits will change. Some satellites will be pulled from one galaxy to the other. Some will be flung into intergalactic space. Some will fall into the galactic centers and be absorbed. The entire satellite system of both galaxies will be reshuffled like a deck of cards. The large and small Magellanic Clouds will face uncertain futures. They orbit the Milky Way now, but Andromeda's gravity might capture them, or they might be ejected entirely. The same fate awaits Andromeda's satellites: chaos and destruction for all the smaller galaxies caught between 2 giants. NASA's Spitzer Space Telescope revealed something invisible to optical telescopes: long filaments of dust spiraling inward toward Andromeda's center. These aren't random clouds. They're organized structures, rivers of material flowing toward the supermassive black hole, like water spiraling down a drain. The filaments stretch thousands of light years. Some originate in the outer spiral arms, where gas is abundant. Others come from intermediate regions. All follow precise paths carved by gravity. The dust grains are tiny, smaller than bacteria, but there are trillions of them. Together, they absorb visible light and re-emit it as infrared radiation. That's what Spitzer detects. Scientists trace these dust streams all the way to the galaxy's core. The paths aren't straight. They curve and twist, following the gravitational potential. Think of a marble rolling toward the center of a funnel. It doesn't fall straight down. It spirals inward, following the slope. These dust streams do the same thing on a galactic scale. The discovery explained a long-standing mystery. How do quiet, supermassive black holes get fed? Active black holes, the ones powering quasars, consume enormous amounts of material. Gas falls in rapidly. The accretion disk blazes with radiation. You can see them across the universe. But quiet black holes like Andromeda's barely glow, yet they must be eating something. Otherwise, they'd be completely dark. The answer is steady, slow feeding. The dust streams deliver material to the central parsec, which is about 3 light-years from the black hole. There, the material forms a small hot disk. The disk feeds the black hole continuously, but the flow rate stays low, just enough to produce faint X-ray emission, not enough to trigger violent activity. Computer simulations published in 2023 tested this idea. Researchers modeled how gas behaves as it spirals inward. They found that if the streams stay within specific size and flow rate constraints, a stable feeding disk forms. The disk doesn't flicker or burst. It glows steadily. The simulations matched observations perfectly. But here's the critical detail. The streams must be narrow. If they're too wide, material falls in as clumps instead of a steady flow. Clumps cause the black hole to flare. Brightness increases, then dims, then increases again. Variability. Andromeda's black hole shows little variability most of the time. That means the streams feeding it must be just the right size. Spitzer's infrared observations confirmed this. The dust filaments are narrow, typically just a few light-years wide. They maintain this width even as they extend thousands of light-years from the center. Somehow, galactic dynamics organize the flow into these narrow channels. The mechanism isn't fully understood, but the observations are clear. Mixed with the dust is gas, mostly hydrogen, some helium, trace amounts of heavier elements. The gas follows the same spiral paths as the dust. As material gets closer to the black hole, gravity accelerates it. Speeds reach thousands of miles per second. Friction between gas layers heats it to millions of degrees. The hot gas begins emitting X-rays. This feeding mechanism differs from galaxy to galaxy. Some galaxies have massive gas reservoirs in their centers. They feed their black holes through different processes. Andromeda's method, using long dust streams, appears optimized for slow, steady accretion. It's elegant, efficient, and it keeps the galaxy's center relatively calm. For now, the black hole doesn't always stay quiet. Sometimes it wakes up. Flares erupt from the center. X-ray brightness spikes, then slowly fades back to baseline. These events tell us the feeding process isn't perfectly smooth. The Chandra X-ray Observatory has watched Andromeda's nucleus since 2009, 15 years of continuous monitoring, the longest X-ray surveillance of any external galaxy's core. Dr. Stephen de Kirby and his team analyzed every observation in the public archive. They constructed a complete light curve, showing how brightness changed over time. Most of the time, the X-ray output remains stable, a baseline level of emission coming from hot gas near the black hole. Count rates stay within a narrow range. This confirms the steady feeding model. Material dribbles in at a constant rate. The black hole consumes it smoothly. No drama. But in 2006, something changed. Brightness jumped, not a subtle increase, a genuine flare. The X-ray flux doubled, then it stayed elevated. The black hole remained in this high state for years. Observations from 2009 through 2016 all showed elevated brightness compared to earlier decades. Then, in 2013, another flare. Brightness spiked even higher. The event lasted several months before declining, but it didn't return to the original baseline. It settled at an intermediate level, higher than pre-2006, but lower than the peak. A gap in observations between 2016 and 2021 makes interpretation difficult. Chandra wasn't looking at Andromeda during those years. Budget constraints and scheduling conflicts meant other targets received priority. When observations resumed in 2022, the black hole was still in an elevated state. Whether this is the tail end of the 2006 flare or the result of subsequent unseen flares remains unknown. What causes these flares? The most likely explanation is clumpy accretion. Despite the narrow dust streams, material doesn't flow with perfect uniformity. Small variations occur. Maybe a molecular cloud in the spiral arms collapsed and sent a pulse of gas inward. Maybe the disk inside the central parsec became temporarily unstable. Something disrupted the smooth feeding. When extra material arrives at the black hole, accretion rate increases. More gas spiraling in means more friction, more heating, more X-ray emission. The flare represents the black hole gorging on a temporary surplus. Once the extra material is consumed, brightness returns toward baseline. The team also measured something called the hardness ratio. This describes the balance between high energy and low energy X-rays. Hard X-rays have shorter wavelengths and higher energies. Soft X-rays have longer wavelengths and lower energies. The ratio reveals the temperature and density of emitting gas. Andromeda's hardness ratio varies. During flares, it shifts toward harder X-rays. This suggests the gas near the black hole gets hotter during feeding bursts. Temperature spikes from a few million degrees to tens of millions of degrees. The exact values depend on accretion rate and geometry. Fast accretion heats gas more efficiently than slow accretion. Comparing these measurements to other galaxies provides context. The Milky Way's supermassive black hole, Sagittarius A star, is even quieter than Andromeda's. It barely flickers. Other galaxies have wildly variable centers. Some change brightness by factors of 10 or more within months. Andromeda falls in the middle, mostly quiet, occasionally active, a moderate eater among supermassive black holes. The flares prove the black hole is awake, not dormant, just patient, waiting for the next meal to arrive down those long dust spirals. Imagine photographing a beach and resolving individual grains of sand. That's what Hubble accomplished with Andromeda. The panchromatic Hubble-Andromeda Treasury, PHAT, is the most detailed image of any external galaxy ever created. The project began in late 2011. It required over 1,000 Hubble orbits. Each orbit lasts about 90 minutes as the telescope circles Earth. During each orbit, Hubble spent precious minutes photographing a tiny section of Andromeda, 411 separate telescope pointings, 7,398 individual exposures. Observations spanned from July 2010 through October 2013. The logistics were staggering. Hubble's field of view is tiny compared to Andromeda's size on the sky, like looking at a city through a drinking straw. To photograph a substantial portion of the galaxy, astronomers had to create a mosaic. Each pointing captured one small tile. The tiles overlapped slightly to ensure no gaps. Later, specialists at the Space Telescope Science Institute stitched all the tiles together into one seamless image. The final mosaic contains 1.5 billion pixels, 1.5 gigapixels. When the full-resolution image was first released, it was one of the largest astronomical images ever published. You can zoom in endlessly. First, you see the whole galaxy. Zoom deeper. Spiral arms resolve into star clusters. Deeper. Individual clusters separate into distinct stars. Deeper still. You can see color differences between stars. Blue giants, red giants, yellow dwarfs, all individually visible. The image shows over 100 million stars. Not galaxies, not clusters. Individual stars. Each one a sun potentially hosting planets. The section photographed spans 61,000 light-years of Andromeda's disk. That's more than half the Milky Way's entire diameter. Yet it represents less than 1/3 of Andromeda's full extent. Scientists used the image to study stellar populations in unprecedented detail. They could measure the ages of stars by their colors and brightnesses. Young blue stars cluster in spiral arms where star formation is active. Older yellow and red stars fill the spaces between arms. By mapping where different ages of stars appear, astronomers reconstructed Andromeda's star formation history. They could see which regions formed stars recently and which have been quiet for billions of years. The image also revealed thousands of star clusters, globular clusters containing hundreds of thousands of stars each, open clusters with just a few thousand members. These clusters are stellar nurseries, places where gas clouds collapse to form many stars at once. Some clusters are billions of years old, ancient relics from when the galaxy was young. Others are just a few million years old, babies by cosmic standards. Dark dust lanes thread through the bright regions. These aren't empty voids, they're dense molecular clouds, so thick with dust that they block visible light from stars behind them. Within these dark lanes, new stars are forming right now. In infrared wavelengths, the clouds glow with heat from embedded protostars, baby stars still surrounded by their birth material. The PHAT image represents more than beautiful photography. It's a scientific goldmine. Researchers published over 150 scientific papers using this data. Studies of stellar evolution, dust properties, star cluster dynamics, spiral arm structure, the galaxy's rotation curve, chemical composition gradients. Each paper extracted new understanding from the 1.5 billion pixels. In January 2025, NASA released an updated mosaic. This version incorporated additional observations taken over the past decade, 600 total telescope pointings. The new mosaic captures 200 million stars, double the original count. It extends coverage farther into the galaxy's outer regions, 200 million resolved stars in a single image. And that's still just a fraction of Andromeda's trillion-star population. Most stars are too faint for even Hubble to detect at 2.5 million light-years distance. But the brightest ones, the giants and supergiants, shine clear as daylight. Each pixel contains a story. Each star lived a unique history. Some were born during that massive merger 2 billion years ago. Others formed recently in collapsing gas clouds. Looking at this image is looking at time itself. The light from these stars has been traveling for 2.5 million years. When it began its journey, early humans were just starting to walk upright in Africa. We're seeing Andromeda's past, but we're looking at our potential future. Andromeda spans 6 times the width of the full moon in Earth's sky. If you could see its full extent with naked eyes, it would dominate autumn nights, but we can't. Human eyes aren't sensitive enough to detect the faint outer regions. We see only the bright central core, a small, fuzzy patch. Unimpressive unless you know what you're looking at. The apparent size versus actual distance creates a fascinating paradox. The galaxy is 2.5 million light-years away, 15 quintillion miles, yet it appears large. The reason is simple. Andromeda is genuinely enormous. Even at that vast distance, its physical size translates to significant angular size on the sky. Angular size is measured in degrees. A full circle contains 360 degrees. The moon spans about half a degree. Your thumb held at arm's length covers roughly 1 degree. Andromeda's visible disk extends roughly 3 degrees. That's 6 moon diameters. In a dark sky, with perfect conditions and adapted eyes, you can perceive the galaxy's elongated shape, not round like a planet, stretched, elliptical. That's because we view it at an angle, not face-on. If the entire gas halo were visible, Andromeda would span over 100 times the moon's diameter. It would stretch from horizon to horizon in certain directions. The Big Dipper would fit inside it multiple times. Every night, a quarter of the sky would be filled with Andromeda's invisible presence. The thought is both beautiful and terrifying. But even without seeing the halo, the visible portion is striking when you know where to look. Autumn and winter offer the best viewing from the northern hemisphere. The galaxy rises in the east during evening hours. By midnight, it passes almost directly overhead for mid-northern latitudes. By dawn, it's setting in the west. Finding Andromeda is easier than most people think. First, locate Cassiopeia, the W-shaped constellation in the northern sky. From the point of the W, draw an imaginary line toward the constellation Perseus. About halfway along that line, you'll spot a faint smudge. That's Andromeda. No telescope needed, just dark skies and patience. Binoculars transform the view. The central bulge brightens into a distinct core. The disk extends visibly on both sides. With a small telescope, you can spot the two companion galaxies, M32 and M110. They appear as fuzzy spots near the main galaxy. Larger telescopes reveal dust lanes, hints of spiral structure, brighter star clouds embedded in the disk. Photography reveals even more. Long exposures capture light that human eyes cannot accumulate. The spiral arms emerge. Pink, star-forming regions glow in hydrogen alpha emission. The full extent of the disk becomes visible. Amateur astrophotographers regularly capture stunning images of Andromeda using backyard equipment. Digital cameras and processing software have democratized deep sky imaging. The proximity is what makes this possible. At 2.5 million light-years, Andromeda is still close enough for ground-based telescopes to resolve structure. Galaxies at 100 million light-years appear as tiny smudges. Galaxies at 1 billion light-years are pinpoints. Andromeda is a giant looming in our neighborhood, close enough to study in detail, close enough to feel personal. That closeness also means we're invested in its fate. This isn't some distant object we'll never interact with. This is our neighbor, our future dance partner. Whether the collision happens or not, Andromeda will shape the evolution of the local group for billions of years. When you look at that faint smudge in the autumn sky, you're seeing across 2.5 million years. You're looking at light that left the galaxy before modern humans existed. The photons traveled through empty space for all that time just to hit your eye, to trigger a response in your brain, to make you aware of something inconceivably distant, yet somehow intimately connected to our cosmic story. Andromeda isn't just out there. It's coming here. Andromeda bleeds metal into space, not solid chunks of iron or copper, atoms, individual atoms of heavy elements forged inside stars and blasted outward by supernovae. This process has been happening for billions of years. The galaxy is slowly ejecting its own guts into the surrounding void. When massive stars exhaust their nuclear fuel, they explode. The detonation releases more energy in seconds than the star emitted during its entire lifetime. Temperatures reach billions of degrees. Every silver ring, every platinum wedding band, they were forged in stellar explosions billions of years ago, then incorporated into the gas cloud that eventually formed our solar system. The supernova ejector doesn't stay in the galactic disk. The explosion is so violent that material escapes at thousands of miles per second. This is faster than the galaxy's escape velocity in many regions. The material punches through the disk and keeps going, into the halo, into intergalactic space. Some of it escapes the galaxy entirely, lost forever. Over Andromeda's lifetime, this process has expelled nearly half of all the heavy elements its stars have created. Half. The galaxy worked for billions of years to build those elements through stellar nucleosynthesis. Then, it threw them away. This seems wasteful, but it's how galaxies evolve. The halo's composition reveals this history. Project Omega didn't just measure the halo's extent, they measured what it's made of. Using spectroscopy on the light from background quasars, the team identified absorption lines corresponding to specific elements: oxygen, carbon, nitrogen, silicon, sulfur, magnesium, all present in the halo at measurable abundances. These elements are called metals in astronomy. The term is confusing because it includes non-metals like oxygen and carbon. In astronomical parlance, anything heavier than helium counts as a metal. Hydrogen and helium were created in the Big Bang. Everything else formed inside stars. So the presence of metals in the halo proves that enriched material has been ejected from the disk. The metallicity isn't uniform. It varies with location. Regions closer to the galactic center show higher metal abundances. Makes sense. The center has more stars packed into a smaller volume, more supernovae, more ejected material. The outer halo is less enriched. Material there comes from stars in the disk's outer regions, where stellar density is lower. Supernovae aren't the only enrichment mechanism. Stellar winds from massive stars also carry material into the halo. Red giants shed their outer layers gradually over millions of years. Planetary nebulae form when sun-like stars eject their envelopes at the end of their lives. All these processes contribute, but supernovae dominate. They're the most violent and most efficient at launching material to high velocities. The enriched halo eventually falls back. Not all of it escapes permanently. Some material reaches maximum height, slows down, and eventually gets pulled back by gravity. This creates a fountain. Gas rises from the disk, cools, falls back. The cycle takes hundreds of millions of years to complete. Each cycle mixes material, enriches the outer disk, spreads heavy elements throughout the galaxy. This is why newer stars contain more metals than older stars. Early generations formed from nearly pure hydrogen and helium. They lived, died, and enriched their surroundings. The next generation incorporated those metals. They formed with slightly higher metallicity, lived, died, enriched further, generation after generation. The metal content gradually increased. Our Sun is a fairly metal-rich star. It formed from material that had already been cycled through many previous stellar generations. The metals in our bodies, carbon, nitrogen, oxygen, calcium, iron, were forged in stars that died before the Sun existed. We are made of recycled stardust. Andromeda's halo is filled with the same stuff. Stardust expelled from 1 trillion suns, and when the halos merge, their metals will mix. For centuries, nobody knew what Andromeda was. A fuzzy patch in the sky, visible to the naked eye on clear nights. Persian astronomer Abd al-Rahman al-Sufi documented it in 964. He called it a little cloud, but he had no idea what he was looking at. As telescopes improved, the mystery deepened. Andromeda showed structure, spiral features. It looked like swirling gas, maybe a nebula inside the Milky Way where stars were forming. Or perhaps a solar system under construction. Nobody imagined the truth that it was an entirely separate galaxy, island universe, billions of stars strong. The idea seemed absurd. By the early 20th century, astronomers split into two camps. One group believed spiral nebulae, including Andromeda, were relatively nearby objects within our galaxy, clouds of gas maybe a few thousand light-years away. The other group proposed something radical. Maybe these nebulae weren't inside our galaxy at all. Maybe they were separate galaxies at enormous distances. On April 26, 1920, two prominent astronomers staged a formal debate. The Great Debate, held at the Smithsonian Museum of Natural History in Washington. Harlow Shapley argued that spiral nebulae were part of the Milky Way. Heber Curtis argued they were external galaxies. The debate focused on observations and measurements. Neither side could prove their case definitively. The data weren't good enough yet. Shapley pointed to the Milky Way's apparent enormous size. Based on his studies of globular clusters, he estimated our galaxy measured 300,000 light-years across. Spiral nebulae, like Andromeda, appeared too small to be comparable galaxies. They must be smaller objects within our own galaxy. His logic was sound given his assumptions. Curtis countered with several observations. First, spiral nebulae showed dark dust lanes similar to those in the Milky Way. This suggested they were disk galaxies seen edge-on. Second, novae had been observed in Andromeda. These stellar explosions appeared much fainter than novae in the Milky Way. If they were intrinsically similar, this meant Andromeda must be much farther away. Third, Andromeda showed a large Doppler shift. It was moving at 300 kilometers per second. If it were inside the Milky Way, such high velocity seemed unlikely. The debate ended without a clear winner. Both sides presented compelling arguments. The question remained unresolved. Astronomers would need better measurements to settle it. Those measurements came a few years later. In 1922, Estonian astronomer Ernst Öpik used a new method. He measured the velocity of stars within Andromeda using spectroscopy. The rotation velocity, combined with the galaxy's apparent size, allowed him to estimate its distance. He calculated 450 kiloparsecs, about 1.5 million light-years, far beyond the Milky Way's boundaries. But Öpik's result was controversial. Many astronomers didn't trust the method. They wanted more direct distance measurements, something definitive. That came in 1925. Edwin Hubble, using the 100-inch Hooker telescope at Mount Wilson Observatory, photographed Andromeda repeatedly. He identified Cepheid variable stars in the galaxy's disk. Cepheids are special stars that pulse in brightness with regular periods. The period correlates directly with the star's intrinsic luminosity. This period-luminosity relationship had been discovered by Henrietta Leavitt. It provided a cosmic yardstick. Measure the period, calculate the true brightness, compare to observed brightness. The difference reveals distance. Hubble found Cepheids with periods indicating they were extremely luminous stars, yet they appeared faint. The only explanation was enormous distance. He calculated Andromeda was roughly 900,000 light-years away. Later refinements adjusted this to about 2.5 million light-years, but the conclusion was clear. Andromeda was a separate galaxy, an entire universe of stars beyond our own. The discovery revolutionized astronomy. The universe was far larger than anyone imagined. The Milky Way wasn't the entire cosmos. It was one galaxy among countless others. Andromeda was our nearest large neighbor in an infinite cosmic ocean. Curtis had been right. Spiral nebulae were island universes, and reaches roughly 260 billion times the sun's luminosity. That's an incomprehensible amount of light. If you could collect all the photons Andromeda emits in all directions for 1 second, you'd have more energy than humanity has used in its entire history. The galaxy is a cosmic lighthouse, but distance diminishes brightness. Light spreads out as it travels. It follows the inverse square law. Double the distance, brightness drops to 1/4. Triple the distance, brightness becomes 1/9 at 2.5 million light-years. The drop is astronomical. Each photon Andromeda emits has only a tiny probability of eventually hitting Earth. Yet enough photons arrive. Not many, just enough. Andromeda's apparent magnitude is 3.4. This is a logarithmic scale where lower numbers mean brighter objects. The faintest stars, visible to the naked eye under perfect conditions, have magnitude 6.5. Andromeda is well above that threshold. It's one of only 10 galaxies visible without telescopes. But here's the catch. Brightness alone doesn't guarantee visibility. Surface brightness matters too. Andromeda spreads its light across 6 times the moon's diameter. The same total light distributed over a large area appears dimmer than if concentrated in a point. This is why Andromeda appears as a faint smudge rather than a brilliant star. If you could compress Andromeda's visible light into a single point, it would shine as a magnitude 3.4 star, easily visible, bright enough to be noticed immediately. But spread across 3 degrees, each tiny patch of the galaxy contributes only faint light. Your eye struggles to detect it. Human vision evolved to detect contrast, differences in brightness between adjacent regions. A star works well, bright point against dark background, high contrast, easy to see. But Andromeda has low contrast. The galaxy glows just slightly brighter than the surrounding sky, especially near cities, where light pollution raises the background brightness. The galaxy vanishes. Not because it got dimmer, because the contrast dropped below detection threshold. This is why Andromeda is easier to see with peripheral vision. The center of your retina, the fovea, contains mostly cone cells. They handle color and fine detail, but aren't very sensitive. The surrounding retina contains more rod cells. They're extremely sensitive, but colorblind. When you look slightly away from Andromeda, its light hits your rods instead of cones. Suddenly, it appears brighter, clearer. Astrophotographers exploit this effect. They use peripheral vision to frame Andromeda through their cameras. Once centered, they look away and capture the image. The galaxy appears far more prominent in photos than to the eye, not because cameras are more sensitive, because long exposures accumulate light over time. Your eye resets constantly. It can't accumulate photons like a camera sensor. The paradox resolves. Andromeda is visible because it's intrinsically bright, but it's difficult to see because its light is spread thin. Distance and surface brightness fight against visibility. Intrinsic luminosity fights for it. The balance is precarious, just barely visible under ideal conditions. In truly dark locations, away from any artificial light, people sometimes notice Andromeda by accident. They look up and see an unfamiliar fuzzy patch, something that wasn't there before. Except it was always there. They just never noticed. Human attention is drawn to bright points. We overlook diffuse glows. Andromeda hides in plain sight, 2.5 million light-years, visible to the naked eye, a galaxy containing 1 trillion suns, reduced to a faint smudge that most people never see. The gas feeding Andromeda's black hole is cool, only a few million degrees Celsius. That sentence sounds insane. Millions of degrees described as cool. But in the context of supermassive black holes, it's accurate. Most active black holes heat their accretion material to tens or hundreds of millions of degrees. Some reach billions. The gas glows white-hot in X-rays. These systems are visible across the universe. Quasars, powered by black holes, devouring huge amounts of matter, shine brighter than entire galaxies. They're cosmic furnaces. Andromeda's black hole is different. When NASA's Chandra X-ray Observatory first imaged the galaxy's core in 1999, scientists expected temperatures around 50 to 100 million degrees. Standard models predicted that much heating. Instead, they measured just a few million degrees, cool by comparison. Dr. Michael Garcia and Dr. Stephen Murray from the Harvard-Smithsonian Center for Astrophysics announced the findings in January 2000. They'd identified the central source. Its X-ray spectrum revealed gas temperature. The low value shocked everyone. Something was wrong with the standard models. Or, something about Andromeda's black hole was unique. To be clear, a few million degrees is still ridiculously hot by everyday standards. Iron melts at 1,500 degrees Celsius. The sun's surface reaches 5,500 degrees. Its core hits 15 million degrees. Andromeda's black hole environment matches stellar core temperatures. Atoms are completely ionized, electrons stripped away. Matter exists as plasma, pure energy, and charged particles. But compared to typical supermassive black hole accretion, it's cool. The question became why? What keeps the temperature down? Several factors contribute. First, accretion rate. Andromeda's black hole consumes very little material, about 1/10,000th of a solar mass per year. That's incredibly slow. Less material falling in means less friction. Less friction means less heating. The gas doesn't reach extreme temperatures because there isn't enough of it colliding violently. Second, the feeding geometry. Remember those long dust streams Spitzer discovered? They deliver material gradually. The gas spirals in, slowly over millions of years. It has time to radiate away some of its thermal energy. By the time it reaches the inner accretion disk, it's already cooled somewhat. Third, magnetic fields. The region around the black hole isn't empty. Magnetic fields thread through the plasma. These fields can tap rotational energy and convert it to radiation. This process, called magnetic braking, removes energy from the gas. Lower energy means lower temperature. The magnetic field essentially provides a cooling mechanism. Fourth, winds. Even quiet black holes produce outflows. Radiation pressure from the hot inner disk pushes some gas outward. This creates a wind. The wind carries away energy and material. The mass that remains in the disk is depleted, again lowering temperatures. All these factors combine to keep Andromeda's central feeding zone relatively cool. But cool is relative. If you could magically transport yourself there, you'd be vaporized instantly. The radiation would tear you apart before heat became an issue. Humans evolved to survive at 300 Kelvin. Andromeda's black hole environment runs at millions of Kelvin, thousands of times hotter than anything in the solar system. The temperature also varies. During flares, when extra material falls in, heating increases. Temperatures can spike to tens of millions of degrees temporarily. The X-ray spectrum hardens. More high-energy photons appear. Then, as the flare subsides, temperatures drop back toward baseline. Comparing Andromeda to the Milky Way reveals similarities. Our galaxy's central black hole, Sagittarius A star, also has cool accretion, same few million-degree temperatures. Both galaxies have quiet, underfed black holes. This isn't coincidence. Similar galaxies produce similar central engines. But not all galaxies are like this. Elliptical galaxies often have much more active centers. They host hotter black holes consuming material rapidly. The difference comes down to gas supply. Spiral galaxies like Andromeda and the Milky Way have most of their gas locked in stars and the disk. Little remains to feed the central black hole. Elliptical galaxies often result from mergers. Mergers stir up gas, provide fresh fuel. The black holes feast. When Andromeda and the Milky Way eventually collide, if they collide, their central black holes will get a major boost. Fresh gas from the merger will flood inward. Accretion rates will skyrocket. Temperatures will soar. Both black holes will become much more active. They'll heat their surrounding gas to hundreds of millions of degrees. The cool phase will end. Enjoy the quiet while it lasts. Earth's future in a merged galaxy is precarious. Computer simulations predict 3 possible outcomes. Most likely, nothing dramatic happens. Our solar system survives intact. The sun keeps its planets. Life continues until the sun dies naturally in about 5 billion years. But there's a twist. The sun's location within the galaxy will probably change. Simulations show a 50% chance we'll be flung 3 times farther from the galactic center. Currently, the sun sits about 26,000 light-years from the Milky Way's core. In a merged galaxy, we might end up 78,000 light-years out, the outer suburbs of Andromeda. What would this mean? Practically nothing for life on Earth. The sun doesn't care where it is in the galaxy. Its nuclear fusion continues regardless. Planetary orbits don't depend on galactic position. Earth would keep circling the sun exactly as it does now. From a physical standpoint, nothing changes. But the night sky would transform dramatically. Currently, the Milky Way band stretches across our sky. A river of stars visible on dark nights. That's our view along the galactic disk. Billions of stars too faint to resolve individually, but collectively glowing as a milky band. From the outer reaches of Andromeda, the view would be different. The galactic center would appear more distant, dimmer. The band of stars would narrow, become less prominent. Instead of feeling surrounded by our galaxy, we'd feel isolated, ejected. The stellar density in the outer regions is much lower than in the inner disk. The space between stars increases. Our nearest neighbors might be twice as far away as they are now. Some stars would be closer, others farther. The rearrangement of orbits during the merger would shuffle stellar positions randomly. But statistically, being farther from the galactic center means lower stellar density, fewer stars nearby, darker skies in some ways, but also a clearer view of extragalactic space. With less intervening material, we'd see distant galaxies more easily. The more disturbing scenario is complete ejection, a 12% chance, not negligible. In those simulations, the solar system gets flung entirely out of the merged galaxy, thrown into intergalactic space. Orphaned, how does this happen? Gravitational interactions during close passes between the galaxies. As stars from both galaxies intermingle, they affect each other's orbits through gravity. Most interactions are gentle, small velocity changes, but occasionally, a star passes through a dense region at just the wrong angle. It gets a gravitational kick, a slingshot effect. If the kick is strong enough and directed outward, the star accelerates beyond the galaxy's escape velocity. It leaves, forever, no turning back. Simulations suggest about 12% of stars in both galaxies will suffer this fate. Roughly 150 billion stars ejected, wandering intergalactic space for eternity. If the Sun becomes one of those ejected stars, Earth's sky would go nearly black at night. No Milky Way band, no galaxy visible above, just scattered points of light. A few hundred stars within a reasonable distance, but most of the sky would be empty, void. The nearest large galaxy, whatever it might be, would appear as a tiny smudge. We'd be alone. Again, this wouldn't affect life on Earth physically. The Sun would shine, Earth would orbit, but psychologically, it would be devastating. Humans are comforted by the sight of stars, the knowledge that we're part of something larger, part of a galaxy, a cosmic community. Ejection would sever that connection. We'd be adrift. The good news? None of this matters for humanity. By the time any merger occurs, Earth will already be dead. The Sun is gradually brightening. In about 1 billion years, increased solar radiation will evaporate Earth's oceans. The atmosphere will thicken with water vapor, runaway greenhouse effect. Temperatures will soar. All complex life will die. By 4 billion years, when the galaxies potentially collide, Earth will be a scorched rock, possibly engulfed entirely if the Sun swells into a red giant. The solar system's fate in a merged galaxy is irrelevant to us. We won't be here to experience it. But for future forms of life, perhaps elsewhere in the galaxy, the ejection of 150 billion stars represents a massive diaspora, a scattering of solar systems across the cosmic void, isolated, alone, drifting through darkness forever. 2 supermassive black holes, 114 million solar masses combined, destined to merge. The collision would be the most violent event in the local group's history, more energetic than all the supernovae in both galaxies combined, more explosive than anything except the Big Bang itself. But the merger wouldn't happen quickly. Black holes don't just crash together. First, they orbit each other for millions of years, gradually spiraling closer as they emit gravitational waves. Those waves carry away energy and angular momentum. The orbit decays. The separation shrinks. Initially, the black holes would sit thousands of light years apart, each orbiting in the merged galaxy's core. The Milky Way's 4 million solar mass black hole, Andromeda's 110 million solar mass giant. They'd feel each other's gravity but remain distant. Their interaction with surrounding stars would dominate early dynamics. Stars passing near either black hole get flung away at high speeds. This is called the gravitational slingshot. Each ejected star carries away energy. That energy comes from the black hole's orbital motion. As stars get slingshot out, the black holes lose energy. They drift closer together. This process is slow, takes tens of millions of years. Eventually, the separation drops to about 1 light year. At this point, star scattering becomes less effective. There aren't enough stars in the immediate vicinity. The black holes need a different mechanism to continue losing energy. That's where gas enters the picture. If enough gas remains in the merged galaxy's core, the black holes will interact with it. Gas friction drags on the orbiting black holes. This is called dynamical friction. It's extremely efficient at close ranges. The black holes plow through the gas. Each passage creates a wake, a trail of disturbed material. The drag from these wakes saps orbital energy. The the separation continues to shrink, from 1 light-year to 1/100th of a light-year, then 1,000th. The black holes are now close enough that their individual event horizons are measurable compared to their separation. They're truly a binary system. Two black holes bound together, orbiting their common center of mass, at separations below about 0.1 light-years. Gravitational wave emission becomes the dominant energy loss mechanism. The black hole's masses accelerate as they orbit. Accelerating masses generate ripples in spacetime. These ripples carry energy. The black holes lose that energy and spiral even closer. The orbital period at this stage might be weeks or months. Two black holes, each containing millions or hundreds of millions of solar masses, whipping around each other once per month. The gravitational waves produced would be detectable by space-based gravitational wave observatories. Future missions like LISA, the Laser Interferometer Space Antenna, would spot them years before merger. As the separation drops below 1 light day, the inspiral accelerates. The black holes orbit each other multiple times per day, then multiple times per hour. The gravitational wave frequency increases. The signal grows louder. Energy pours out as space-time itself vibrates. Finally, the event horizons touch, merger. In less than a second, the two black holes coalesce into one. The combined mass is slightly less than the sum of the original masses. The difference converted entirely to gravitational wave energy. About 10% of the total mass might be radiated. That's over 10 million solar masses worth of energy released in gravitational waves during the final moments. For comparison, the Sun outputs about 2 solar masses worth of energy over its entire 10 billion year lifetime. This black hole merger would release 5 million times more energy in under a second. The space-time around the merger would shudder. Ripples would propagate across the universe at the speed of light. The final merged black hole would be highly distorted, spinning rapidly, event horizon wobbling like a struck bell. Over the next few hours, it would settle, emit additional gravitational waves as it rings down to a stable configuration. Then it would go quiet. A single supermassive black hole at the center of Andromeda. 114 million solar masses, waiting for its next meal. This entire process, from initial orbit to final merger, takes between 10 and 20 million years, according to simulations, depending on gas availability, depending on stellar density, depending on many factors. But the end result is certain. Two black holes cannot remain binary forever. Gravitational wave emission guarantees they will merge. Unless the galaxies don't collide, then the black holes never meet. They remain in separate galaxies, forever alone. Imagine standing on a rocky planet 4 billion years from now. Not Earth. Earth is dead. Oceans boiled away. Atmosphere stripped, but somewhere else. A world orbiting a younger star, farther from the galactic center, still habitable. You look up. The sky is chaos. Two galaxies interpenetrate. The Milky Way and Andromeda are colliding. This is their first close pass. Not the final merger yet, but close enough for spectacular effects. Andromeda dominates half the sky. No longer a faint smudge, a massive spiral, stretching from horizon to horizon. Individual spiral arms resolved, bright star clusters visible as glowing knots. The galaxy's core blazes like a second moon, except it's not reflected light. It's the combined luminosity of billions of stars compressed into a small angular area. The Milky Way band still crosses the sky, but distorted, warped. Tidal forces from Andromeda are pulling it, stretching it. In some directions, the band brightens as stars get compressed. In others, it thins as stars are drawn away. The familiar constellations are gone, rearranged. The Sun, if it still exists, sits in a completely different region of the sky than 4 billion years earlier. New star-forming regions flare across both galaxies. Where gas clouds collide, shock compression triggers massive bursts of star formation. These regions glow pink with hydrogen emission. thousands of them scattered throughout both galaxies. The rate of star formation is 100 times higher than normal. The galaxies are being transformed. Supernovae erupt constantly. With so much rapid star formation, many massive stars reach the end of their lives quickly. Explosions light up the sky. On average, several supernovae visible to the naked eye every year, sometimes multiple per month, each one brighter than Venus, some brighter than the full moon. They fade over weeks, then disappear. But new ones replace them. The sky never. Starlight would illuminate the landscape. Dim, ghostly, but present. Over the next few billion years, the galaxies would separate, swing past each other, then return for another pass. Each encounter would further distort both structures. The spiral arms would shred. Stars would be flung into new orbits. The organized rotation of both galaxies would become randomized. Chaotic motion would replace orderly spirals. Eventually, around 6 to 10 billion years from the first close pass, the galaxies would lose enough orbital energy to merge completely. They'd fall together, interpenetrate fully, become one. The sky would transform again, no longer two distinct galaxies, one giant elliptical blob, less structure, more uniform, but brighter, all those stars mixing together. The supermassive black holes would sink toward the center, observable as a bright point of light, the active nucleus. As gas falls into the binary black holes, they'd produce intense radiation, maybe a quasar, briefly illuminating the merged galaxy, brighter than billions of stars. Then, settling, quieting. Far future civilizations, if any exist, would study the merger. They'd analyze spectra, track stellar populations, map the gravitational potential, try to reconstruct what the original galaxies looked like before collision. Archaeoastronomy, reading the fossil record written in stellar orbits and chemical abundances. They'd discover that the two galaxies approached each other for billions of years, that their halos touched long before visible disks met, that smaller satellite galaxies were destroyed during the process. The Large Magellanic Cloud consumed, M32 absorbed, all merged into the final product, and they'd look outward, toward other galaxies, wondering if any would merge with Andromeda in the even more distant future, wondering if the process ever ends, or if galaxies continue consuming each other until only a few giants remain, swimming in a universe growing ever emptier as dark energy pulls everything apart. The view from Earth in 4 billion years doesn't exist. Earth won't be there, but the view from somewhere will be spectacular, assuming anyone is watching, assuming life survives long enough to witness the collision, assuming consciousness persists across the vast timescales required. Two galaxies colliding, 1 trillion stars rearranging themselves across millions of years. The biggest show the local group will ever produce. Whether anyone watches or not, it will happen. Gravity doesn't need an audience. It just acts, relentlessly, inevitably, until two become one. And Andromeda is already touching us.